In this video, we're going to talk about continuity. Our objectives will be to define continuity at a point, to discuss and analyze continuity of polynomial and rational functions, to discuss limit laws of composite functions, to discuss continuity on an interval and define all appropriate intervals of continuity, to discuss continuity of functions involving roots, transcendental functions, and inverse functions. We probably won't do this for this course. I'll just be talking about roots probably, and learn the intermediate value theorem and discuss how it applies to real world situations. So let's go ahead and if we need to, we'll come back to this when we get to derivatives, because the intermediate value theorem really has to do with derivatives. Derivatives build on the idea of continuity. So I think we'll come back to this. But we'll see if we get to it at the end of the notes today. All right, so let's first define continuity at a point. And the three cases of a discontinuity, and then we'll create a continuity checklist for determining continuity at a point. This is kind of our outline for today. Then we're going to define continuity on an interval by talking about continuity rules, discuss continuity of polynomial and rational functions. They're going to be continuous on their entire domain. Discuss continuity of a function that's a composite function and how we try and determine what intervals that composite function will be continuous on based off of the intervals of continuity of the two functions which are being composed. We'll define continuity on an interval and discuss discontinuities that happen at endpoints and midpoints, and then discuss continuity of other important functions, specifically roots, and then I don't think we're going to get into transcendental and inverse functions, but we'll see. If we do any transcendental functions, it'll be e to the x. So we may talk about that, but we're not going to talk about any trig functions, for example, which are transcendental functions, because we do not do trigonometry in this version of calculus. We focus only on power functions, exponential functions, and logarithmic functions, basically. So rational functions are in there with the power functions too, as well as radicals and other things. All right, so the concept of continuity is a really important one in calculus. Like I said, you need continuity before you can talk about a derivative. So before, you likely thought of it as the ability to draw the graph of a function without lifting your pencil up off the paper. And that was a good layman's way to talk about it. But we'll define continuity more precisely now using the idea of limits. And we'll make a distinction between continuity on an interval, which you found intervals in the past over which the function was continuous, and what it means to have continuity of a function at a point, or continuity on a function's domain. But we really want to start with continuity at a point. What does it mean to be continuous at a point? That's where we need to start everything, because the point's the smallest element here that we can talk about in a set would be a single point. And then we can build intervals with multiple points together. So continuity at a point, a function f is continuous. At x equals a, if the limit as x approaches a of f of x is equal to f of a. Get that to finish right in there in just a second. There we go. So when does a limit exist? we need to remember that the limit exists when the limit as x approaches a from the left is equal to the limit as x approaches a from the right is equal to a finite value L. L is finite, right? So our checklist here for continuity. Continuity checklist, which I'll abbreviate CCL, moving forward is going to have little Roman numeral 1, F of, and I'm going to use C's instead of A's because your book uses C's. So F of A exists. Roman numeral 2, the limit as x approaches C of F of X exists. Roman numeral 3 here, the limit as x approaches C of F of X is equal to F of C. Now we're going to use A's in these notes instead of C's because this is originally based off of another textbook than the one that you're using right now. That's okay. All the definitions and everything are the same. Just don't get confused that A is a constant, so is C, but sometimes we want C to be something else in these notes. So we're not going to use it to be the thing that X is approaching usually here. So got a function that looks like this. And we have a point here that I'm going to put in green. It's right here. And this value there. And that value there. That this is going to be F of A here. And this is X equals A here is that dotted line. This function here is F of X. So we see that the limit as I approach X equals A from the left and the right is F of A, and F of A exists here. So this part of the graph right here, right around A, is I'm able to draw that piece without picking my pencil up off the paper because the limit from the left and the limit from the right equal the same thing and they equal the function value. So I can just draw that part of the graph. It's continuous there. So what this tells us here is if the function is continuous and we want to find the limit here, direct substitution works for all points for which the function is continuous. So we've seen several examples of continuous functions at a point. In the case of continuity, the more interesting dynamics occur at points where the function is not continuous at a point, which would be points of discontinuity. So let's talk about the different types of discontinuity that we can have. First, we have discontinuity with a hole, and that hole can come about where there is a point defined apart from the function here, like we see here in this first graph, or that point doesn't need to be there at all, and there can just be an open hole there. So right here, we have limit as x approaches 3 from the left of this g of x right here. We already called the one above this f of x, so we'll call this one g of x is equal to 1. And the limit as x approaches 3 from the right of g of x is also equal to 1. So that passes continuity checklist number 2 is okay, but we have right here that G of 3 is equal to, it's supposed to be equal to 5. Sorry that that's not quite lined up there, but it's supposed to be lined up there. So that passes continuity checklist number 1. Check, right? It's got 1 and 2, but now we need to think about continuity checklist number 3 here. So this continuity at x equals 3, because limit as x approaches 3 of g of x is not equal to g of 3. If we look at the limit here, 1 is not equal to 5. So right here, we have violated continuity checklist item 3, right? I should be calling these Roman numerals because of your book. So item number 2 and 1, like that. So there we go. If I mess up and start using number 1, number 2, and number 3, because that's how I have it written down in my notes, just replace that with a Roman numeral 1, Roman numeral 2, and Roman numeral 3. So I'm just going to look at a graph here. I'm not going to tell you what this graph is because it's actually based off of a trig function. But I'm just going to draw a graph here that's going to look funny. And it's going to have an open circle right here at the point 0, 1. And it's down and up, and it keeps going kind of like that, where it's going up and down, and it's getting less height as it goes up and down, and it's going forever like that. And this is doing the same thing. It's symmetric here, and it's going like that. So I'm going to tell you that as I come close to 0 here, the limit as x approaches 0 of, I'll call this function h of x. As I come from the left, it equals 1. The limit as x approaches 0 from the right of h of x is also equal to 1. So, but I've got a problem right away that h of 0 is undefined. So it's discontinuous there because it violates continuity checklist part 1. So we're fine with continuity checklist part 2, and we can't have part 3 violated, or we can't have a part 3. It violates part 1 and part 3. 1 and 3 are violated because there is no function value there. So, all right, let's pick up here and talk about a piecewise defined function here. F of x is going to be equal to 1 when x is between 0 included and 1 not included. It's equal to 2 for x is between 1 included and 2 not included, and is equal to 3 for x is between 2 included and 3 not included. So I have this nice graph that reminds me of the greatest integer function, though it's been shifted a little bit. So I have 1, 2, and 3. Hopefully you talked about the greatest integer function in pre-calculus. It was supposed to be one of your parent graphs in pre-calculus part 1 that you talked about, that you needed conceptually to solve some application problems where your answers needed to be in whole units, that it didn't make sense for you to produce a fraction of a car or to have a fraction of a person for your population or things like that. So there's 1, there's 2, there's 3. Lots of times we won't be told we have to use this type of a function, but we will have to logically infer that we need this type of a function when we are talking about production of things. Also, if you have to pay in, say, dollar bills, you're not allowed to pay with any change. You are going to pay, $1 until it's a certain amount of money. If it's between $0 and $1, you're going to pay with $1. And then as soon as it's over $1 and up to $2, you would pay with $2. Now this would be the other way. It would be open on this side and closed on that side. In the case I'm talking about paying with dollar bills, but you get the idea that you'd have these jumps like this if you had it where no change was allowed and you just had to pay in dollars. But that's how it would work out. So let's go ahead and figure out, maybe right now, let's talk about at 1, is there a discontinuity at 1? So f of 1 is equal to 2. Limit of, we're calling this f of x, as x approaches 1 from the left is equal to 1. Limit as x approaches 1 from the right is equal to 2. They're not equal to one another. So the limit as x approaches 1 of f of x does not exist. And continuity checklist part 2 is violated at x equals 1. We're going to see the same thing. Same for x equals 2, right? And then we're going to have a different type of discontinuity for x equals 3, discontinuous at x equals 3 because f of 3 is undefined, which breaks continuity checklist part 1. So we have 3 different discontinuities here that happen at 1, 2, and 3, right? You may also consider here that it's discontinuous at 0 because there's no activity from the left for the limit to exist. So talk to your teacher about if your teacher wants you to say that this graph here is only one-sided here and doesn't have a limit from the left, and if that makes it discontinuous there. Different textbooks and different teachers disagree on whether to look at numbers that are outside of the domain to determine continuity. So anyways, they may want you to just look at the one-sided limit here for this, depending on your textbook definition and your notes that you get in class from your teacher. So we'll talk about that later. That's actually one of the things that we're specifically going to talk about in the notes here, is how you may only be continuous from one side. So recall the negative power function, the reciprocal function, f of x is equal to 1 over x, and then this is the negative odd power parent function. This is the negative even power parent function. So we're going to look first at f of x is equal to 1 over x, the reciprocal function, which looks kind of like this. Not the best at drawing it, but you should have it in your parent graphs, your library of functions in your book. And you can go back and look at the pre-calculus videos if you would like to see Some more on that. There's a horizontal asymptote at y equals 0. There's a vertical asymptote at x equals 0. So the limit as x approaches 0 from the left of 1 over x is equal to negative infinity, not a number that's a finite number L, so this limit really does not exist. And the limit as x approaches 0 from the right of 1 over x is equal to positive infinity, which again does not exist. We're going to cheat sometimes and talk about limits existing at infinity or negative infinity if both sides are doing the same thing, even if it's not defined at that point. We also say, f of 0 is undefined. So we got all kinds of problems going on here that we violated continuity checklist part 2. With the limit not existing here, we violated continuity checklist part 1 because the function doesn't exist there. And so that means that continuity checklist part 3 is also violated. So we just are all around bad here, right, for this one. So let's move on and actually look at an example of something off to the side here. I'm going to say as an example, what would it be like with f of x is equal to 1 over x plus 4 minus 9. There's going to be a vertical asymptote at x equals negative 4. And so that means that it will be discontinuous at x equals negative 4, since f of negative 4 is undefined, right? And that's as much as we need to know to just find that discontinuity if we see a rational function like that. Looking at that even power function, even powered reciprocal like that, 1 over x squared, just to remind you what that looks like, that it goes to positive infinity for both pieces. It also has the horizontal asymptote at y equals 0. It has the vertical asymptote at x equals 0. It just goes to infinity on both sides. Limit as x approaches 0 from the left of g of x is equal to a positive infinity, which the limit does not exist because it increases with that bound. Limit as x approaches 0 from the right of g of x is equal to infinity, which does not exist because it increases with that bound. So continuity checklist number 2 is violated because the limit doesn't exist. Continuity checklist number 1 is violated because it's undefined at g of 0. So that means continuity checklist part 3 is also violated. Anytime that part 1 or part 2 is violated, then part 3 is automatically violated. But part 3 can be violated even if part 1 and part 2 are not violated if there is a jump discontinuity in the graph. So let's go ahead and let's see if we can get this checklist that we've been talking about all narrowed down here. So based on the patterns we see above, in detailing 3 different types of discontinuities, we can create the following checklist to determine if a function is continuous at a point. A function f is continuous at x equals a if limit of f of x as x approaches a is equal to f of a. So our continuity checklist we've been working with, a function f of x is continuous at a point x equals a if the following 3 conditions are true. Continuity checklist item number 1, f of a is defined. Point 2, limit of f of x as x approaches a exists. And point 3, the limit is equal to the function value there. Limit as x approaches a of f of x. Sorry, limit of f of x as x approaches a is equal to f of a. So determine whether or not the following functions are continuous at the given point, x equals a. If not, state the condition on the continuity checklist that is violated. So we know that we can't divide by 0. It's not in the domain. I'm not sure whether it's a whole or a vertical asymptote. That doesn't matter though. F of 1 is undefined. So continuity checklist number 1 is violated. Let's see if 2 is violated here. F of x is going to be equal to 3x. Yeah, I can't factor the top there. So we're going to have a we don't need to check anything else at that point. Once part 1 is violated, that's enough. We know part 3 will also be violated. I think that we're actually going to be able to get numbers from the left and the right here, and the 2 won't be violated. So what type of continuity is this? It's either a whole or an asymptote. The question is, if we write f of x equal to 3x squared plus 2x plus 1 over x minus 1, can we factor the numerator so that x minus 1 is a factor? So let's go back to synthetic division and say, if I put 1 on the outside and I want it to be a 0 of 3, 2, and 1, I know if these are all positive numbers here, there should be no positive roots because this is going to be getting bigger and bigger and bigger. This is not 0. So x minus 1 is not a factor. And as soon as I know that x minus 1 is not a factor, then I know that there is a vertical asymptote at x equals 1, because for there to be a whole, there would have to be a common factor of x minus 1 in the top and bottom that cancels. So let's go ahead and let's look at another example here. F of x is equal to x squared when x is greater than or equal to 1. So this is at x equals 1 there. And then x cubed when x is less than 1. So we have something that's at x equals 1. We're going to have the point 1, and then 1 squared is 1. This is going to give us a point. We're going to have 1, 1, and this will be a whole here. So let's draw the part with the whole first. 1, 1, and it's going to go through 0, 0, -1, -1, and it's going to be a cubic function like this. And it's going to go down like so. And then we have a piece over here that's going to be quadratic, and it's going to keep going up and up to 4, and so on like that. All right. So this is y equals x squared, and this is y equals x cubed on this side. X less than 1, x greater than 1, like that. Now we're going to fill up that hole because this point fills up that hole. My limit as I come from the left and the right is equal to 1. And my function value, f of 1, is equal to 1. Limit as x approaches 1 from the left equals limit as x approaches 1 from the right is equal to 1. And limit as x approaches 1 of f of x is equal to f of 1 is equal to 1. So it is continuous at x equals 1. The reason I only tested this boundary value is I knew that x squared is continuous, is a continuous function, and x cubed is a continuous function. So I'm not worried about all the other interior points here. I know that these are continuous polynomial functions. We'll get there. I'm only interested in this boundary point of, do they line up with one another, and did the whole get plugged up by the point? That's really the only interesting point for me to test in this, because I know that I can draw x squared without picking my pencil up off the paper, and x cubed without picking my pencil up off the paper. The question was really here, are the limit from the left and the right going to be the same thing? And they were. So let's go ahead and let's look at this next example here. And this is a very common type of problem in calculus, where we want to find a function. We want to make a function here in this piecewise defined function. We want to find a value for a where this is going to be continuous. So first things first, let's find what f of 1 equals. Sorry, f of -1. So f of -1 is going to be defined by that top value there. It's going to be 1 plus 2 is 3. So now that means that I have to make, I already know that that's the limit as I come from the left, because I used that top function. So the limit as x approaches -1 from the left, we know is 3. We just did the work from that. Limit as x approaches -1 from the right is going to be a times -1 cubed minus 9 is equal to a negative a minus 9. And so now for part 3, I need to make the function value equal the limit here. So negative a minus 9 needs to be equal to 3. Add 9 to both sides, and negative a is equal to 12, and a has to be a negative 12. All right. Let's keep going here. So in this example, we want to see if f of x is going to be continuous at x equals 1. Is it going to be continuous at x equals -1? If not, what parts of the continuity checklist are violated? So let's factor this first. X minus 1, x minus 3 will give me x squared minus 4x plus 3. And I have x minus 1 and x plus 1. So this is equal to x minus 3 over x plus 1. As long as x is not equal to 1, I cannot change the domain of my original function. I still need to exclude x equals 1, because 0 over 0 is still undefined. But I can define every other point other than x equals 1 with this piece. I can also use this piece here, which will be continuous at x equals 1, to figure out where the hole will be at x equals 1. I know there's a point discontinuity there, which is a hole in the graph. But there's an infinite discontinuity vertical asymptote at x equals -1. So those are my two classifications really in calculus of discontinuities. There's a point discontinuity, which is a hole, and there's infinite discontinuities, which are jumps or vertical asymptotes. So this is going to be a point discontinuity whole at x equals 1, and the whole's coordinates are at 1, and then -2/2 is -1. So you should be able to actually identify that and make it a part of your graph. There's an infinite discontinuity specifically a vertical asymptote at the equation x equals -1. So we know that continuity checklist number 1 is violated here. We know that continuity checklist number 1 and 2 are violated here because there's a vertical asymptote here. The limit actually is going to exist here. So I'll say number 1 and number 3 are violated here. Number 1, number 2, and number 3 are violated here. All right. Let's move on and let's talk about being continuous on an interval now. So we'll use continuity rules to talk about intervals over which a function is continuous. If f and g are continuous at a point x equals a, then the following functions are also continuous at x equals a. The sum and difference of those two functions that are continuous at x equals a will also be continuous at x equals a. A constant multiple times the continuous function where c is any constant will also be continuous there. The product and quotient of those functions there will also be continuous provided that the denominator of the quotient is not equal to 0 and any positive integer n, the continuous function raised to the nth power will also be continuous at x equals a. So let's consider f of x is equal to x and g of x is equal to x squared. Both functions are continuous on -infinity to infinity. Just to verify that, there's y equals x, and it goes from -infinity to infinity. I can draw the whole thing without picking my pencil up off the paper. And there's x squared. I can go all the way to the left, all the way to the right without picking my pencil up off the paper. Is 3 times f of x. We'll call this one f of x, and we'll call this one g of x. Is 3 times f of x continuous? Yes. Look at rule number 2, right? Since f of x is continuous everywhere, three times f of x is also continuous everywhere. So I'm just going to make the slope greater like this with 3 times f of x, but it's still going to be continuous. What about f plus g? So I don't even imagine what that's going to look like, but that's rule number 1. So yes, rule number 1. And since f and g are continuous on -infinity to infinity, f plus g is continuous negative infinity to infinity. What about f divided by g? It'll be continuous everywhere other than at 0. Continuous everywhere except x equals 0, because g of 0 equals 0, and we can't divide by 0. That was the only 0 of g of x that I need to worry about. So we're going to be continuous on the intervals from negative infinity to 0, union 0 to infinity, but we'll be discontinuous at x equals 0. So let's keep going here. A polynomial is continuous on its entire domain, which will be from negative infinity to infinity. Examples of polynomials would be things that look like y equals x squared plus 4x minus 1, or y equals x cubed minus x plus 4. I don't need to have all the powers represented. You're going to see decreasing powers of whole number exponents on x with real number coefficients. A rational function, the quotient of two polynomial functions, is continuous for all x on its domain. So for example, y equals x squared plus 4 over x minus 1 is going to be discontinuous at x equals 1. Division by 0 is the problem there, right? So its domain is negative infinity to positive 1, union 1 to infinity, and it's continuous on that entire domain of negative infinity to 1, union 1 to infinity. State the interval of continuity for the following. This is a polynomial. So it's continuous on negative infinity to infinity. I don't even have anything to check there. Rational function here, I'm going to factor the denominator and turn that into x minus 3 times x minus 4. And I'm going to have that this is going to be x cannot be equal to 3 and x cannot be equal to 4. So we are going to be discontinuous at those two values. Let's look at that on the number line. Move these 2 points, but I'm okay everywhere in between. So continuous on negative infinity to 3, union 3 to 4, union 4 to infinity. We had this earlier example here from lecture 4. Limit as x approaches 2 of x squared minus 6x plus 8 over x squared minus 4. This was the last page of what we did. Remember, we simplified with algebra, and we said that the limit was x minus 2 times x minus 4 over x minus 2, x plus 2. I forgot to write my limit symbol out front of here. And that since I can remove that discontinuity, that was a removable discontinuity or point discontinuity. I didn't talk about that up here. Let me state that all the way up here where I was talking about a point discontinuity. We can also call this a removable discontinuity. This infinite discontinuity is a type of non-removable discontinuity. So we have a removable discontinuity here because we actually can cancel it out and remove it. This is the limit as x approaches 2 of x minus 4 over x plus 2 is going to be 2 minus 4 over 2 plus 2 is a negative 2 over 4 is a negative 1/2. Consider now as we approach negative 2 instead. So this would be limit as x approaches negative 2 of x minus 4 over x plus 2, x not equal to 2. This is going to be a negative 6 over 0 is going to be that limit does not exist. It's an infinite discontinuity. It's actually going to be, depend on which side I'm coming from, it's going to look something like this at negative 2. There's a vertical asymptote there, and we have a piece that is coming this way, actually comes down to negative 1/2 at x equals 2. At x equals 0, we have a negative 2. So we have negative 2, and it comes back up this way. It crosses at 4. Interesting. 4. And then as I get close from the right, this is negative down here. And it's going that way, and then has that hole, and then crosses right there, and then is going to come back. It's going to come towards y equals 1 here from the bottom. And then this piece over here is going to be a negative over a negative. It's going to be a positive. It's going to be like that at negative 1. The limit does not exist since the function has a vertical asymptote. At x equals negative 2. Right. Switch over here. Find my place. Ready to talk about compositions of functions. Just go back real quickly. Make sure this was, what was that one where we were solving for a? Right there, yes, negative 12. All right. And ready to define continuity on an interval, point C. So for a composition of functions, f of g of x, which we can write f of g of x, we won't always have specific functions, f of x and g of x. You want to apply this concept in general. Determine the interval of continuity of the function, f of g. So let's go ahead and find the composition right now, which is going to be x, 2x plus 3, quantity squared plus 1 is 4x squared plus 6x times 2 is 12x plus 9 plus 1 is 4x squared plus 12x plus 10. So we know that f of x is continuous on negative infinity to infinity since a polynomial. G is also a polynomial of degree 1 that's continuous on negative infinity to infinity. And f of g of x, we see here by the composition is also a polynomial that'll be continuous on negative infinity to infinity. Let's look at square root of x and for f of x and x minus 3 for g of x. So f is continuous on 0 to infinity. We're not putting a hard bracket there because we're not doing one-sided limits in this book. Your textbook that you're using may be a little different. So we're going to take a look now at what happens when I take the square root of x minus 3, and that has a domain of x needs to be greater than or equal to 3. So f of g is going to be continuous on 3 to infinity, like that. So our theorem here tells us if g is continuous at x equals a, and f is continuous at g of a, then the composite function f of g of x is continuous at x equals a. For limits of composite functions, if g is continuous at x equals a, and f is continuous at g of a, then limit as x approaches a of f of g of x is equal to f of limit as x approaches a of g of x is equal to f of g of a. And if limit as x approaches a of g of x is equal to L and f is continuous at L, then limit as x approaches a of f of g of x is equal to f of limit as x approaches a of g of x is equal to f of L. We'll use that to our advantage here in just a second. So let's find the limit as x approaches 0 of x to the 4th minus 2x plus 2 over x to the 6th plus 2x to the 4th plus 1 raised to the 10th power. Well, we see that we're not going to get 0 in the denominator here, so this limit is going to exist in the inner function here. And the easiest thing is to find this limit as x approaches 0 and then raise it to the 10th power. So I'm going to take the limit of the inside, x to the 4th minus 2x plus 2 over x to the 6th plus 2x to the 4th plus 1 raised to the 10th is going to be 2 over 1 raised to the 10th. 2 to the 10th is 1024. All right. I guess we just wanted to find f and g here. Not find the limit, but our f of x is going to be our outer function, will be x to the 10th. G of x is going to be our inner function, is going to be x to the 4th minus 2x plus 2 over x to the 6th plus 2x to the 4th plus 1. And we can find that composition. Now we're going to use the theorem that I just used above. So let me get rid of this. Do that in the next step. I just read the prompt wrong. If you want to check this, you can actually plug g into x there and you'll get the original function. So again, we're going to take limit as x approaches 0 of x to the 4th minus 2x plus 2 over x to the 6th plus 2x to the 4th plus 1. And then we'll raise that to the 10th. And that's going to be 2 over 1 raised to the 10th is going to be 2 to the 10th is 1024, as I mentioned before. Is the function continuous at x equals 0? Yes. Yes, it is. Because f of 0 is equal to 1024 if we would go and plug 0 into the original. And the limit as x approaches 0 from the left of f of g of x is equal to the limit as x approaches 0 from the right of f of g of x is equal to f of g of 10, f of g of 0, like that, is equal to 1024. There we go. So is f of x continuous at x equals 4? Yes, because I didn't leave space for that, but let me write that up here. Is f of x continuous at x equals 4? Yes, because, sorry, if f of x is square root of x, I'm saying. Is f of x equals the square root of x continuous at x equals 4? Yes, because f of x equals the square root of x is continuous on the interval from 0 to infinity, and 4 is within that interval. So don't get mixed up because square root functions are not continuous at the vertex at the end. Everywhere in the middle, they're continuous. Let's define continuity on an interval and discuss discontinuity at endpoints and midpoints. Continuity on an interval, a function f is continuous from the right, called right continuous at a if limit as x approaches a from the right of f of x is equal to f of a, and the function f is continuous from the left, called left continuous at a if limit as x approaches a from the left of f of x is equal to f of a. So example 1 of a right continuous function would be something that looks like so, where open circle and f of x goes like that. Sorry, not a hole there, but a point there. So this is right continuous. What I wrote just a second ago, not right continuous, because you still have that hole if you're coming from the right there. So you have to have a point here and have a limit from the right. For left continuous, we would have something that would look like this, but we would not have something right continuous if it were a hole on the right hand side. So we have to have an a, f of a here. We have the limit as x approaches a from the left. F of x is equal to f of a here. We have an a, f of a here. We have limit as x approaches a from the right of f of x is equal to f of a here. All right. Now that we've talked about that, continuity on an interval, a function f is continuous on an interval I if it is continuous at all points I. If I contains endpoints, the I is the interval, closed interval 1 to 4, for instance. Continuity on I means f is continuous from the right and the left at the appropriate endpoints. So for all x equals a, f of a exists. The limit as x approaches a of f of x exists. The limit as x approaches a of f of x equals f of a. Those would be our three main things that we would say, but if we have closed endpoints there, we need to check for left continuous at the right endpoint and right continuous at the left endpoint. That's an easy mistake to make. Fix that in the notes there. that you need to be able to come from the left-hand side at the right endpoint and from the right-hand side at the left endpoint. Define continuity on an interval. So discuss continuity of other important functions, like functions involving roots. And okay, we are going to talk about e to the x and ln of x. So we will talk about some transcendental functions. So g of x is equal to e to the x and f of x is equal to ln of x. Is ln of x going to be continuous at x equals -2? No, because the domain of ln of x is 0 not included to infinity. -2 is not in the domain. So we violate continuity checklist number 1 there and can't be continuous there. Let's look at these graphs. E to the x is going to be continuous on its entire domain of -infinity to infinity. Like I just said, ln of x is going to be continuous on its entire domain of 0 to infinity. All exponential functions are going to look like this and have the same idea for its domain and where it's continuous. Some will be rising to the right, some will be falling to the right, depending on whether the base is greater than 1 or between 0 and 1. Logs in general will look like this if they have bases that are greater than 1. And they may be falling to the right otherwise. But here we go. Let's determine the values of x for which the following function is undefined. So we would have to say e to the x minus 1 is equal to 0, and then e to the x is equal to 1, and then ln of e to the x is equal to ln of 1, and x is equal to 0, which is what we just did right down here to get that answer. So in that case, that's going to be division by 0. So we're going to be discontinuous at x equals 0 because of division by 0. F of 0 is undefined, right? So we have to remove 0 from the domain and we get -infinity to 0 union 0 to infinity. Let's say let's try this in this space. So if we have state the intervals of continuity, f of x is equal to x to the 4th minus 3x squared. 2x plus 1 is continuous on -infinity to infinity because it's a polynomial. And f of x is equal to x squared plus 2x plus 7 over x minus 1 is going to be continuous on its domain, which is -infinity to 1 union 1 to infinity. All right, with functions involving roots, if n is a positive integer and n is an odd positive integer, then the function of x raised to the 1 over n is continuous at all points for which f of x is continuous, but we have to watch out for when n is positive and even, then we are only continuous for f of x to the 1 over n at all points for which f is continuous and f of x is greater than 0. Let's see, greater than, if it's equal to 0, we're not continuous there because we only have a limit from one side. So that's why it doesn't say or equal to 0 here. But for all the parts where where the square root was greater, had a inside that was greater than 0, we're continuous on all this part over here. We're just not continuous at that point right there. That's the vertex. So for what values of x are the functions continuous? This is continuous on the interval from 0 to infinity because we need x to be greater than 0. Here we're continuous on negative infinity to infinity since this index is odd. Here we're continuous on -3 to infinity. We set the inside equal to 0 and solve to get our left endpoint. Here probably would be best to look at a graph of this function to know this is the top half of that circle there. And we are not going to be continuous at either of the endpoints there where we're going to have 0 inside the root. So we're going to be continuous from -3 to 3. We can solve that inequality, that polynomial inequality, to say that this needs to be greater than 0, which makes -x squared greater than -9. Sorry, let's flip this around this way. X squared minus 9 less than 0 by dividing both sides by -1. This is x plus 3 times x minus 3 less than 0. Set up my number line here, -3, 3. I'm going to exclude those points because they're I'm not allowed to have 0 there. If I stick in a number less than -3, I get a negative times a negative as a positive. If I stick in a number between -3 and 3, I get a positive times a negative as a negative. If I stick in a number greater than 3, I get a positive times a positive as a positive. I want negative numbers, so I'm going to shade in here to get my answer of -3 to 3, just like when I graphed. Let's skip down here to f of x is equal to x squared minus 2x plus 4 to the 2/3. So this really looks like the cube root of x squared minus 2x plus 4 squared. There's no problem spots for that because it's a polynomial that's continuous everywhere. And this is odd. So our interval of continuity is going to be -infinity to infinity. Let's look at this next one here. F of x is equal to the square root of x squared plus 2x plus 7 over x minus 1. So we need x squared plus 2x plus 7 over x minus 1 to be greater than 0, since it's a square root for us to be continuous. And we need to think about the quadratic formula here or complete the square. +1 plus 1. Okay, that's fine. That's always going to be a positive. If we look at the graph here, this is always greater than 0. And this will be so positive divided by, and I just need to make sure that that's not negative. So x needs to be have 1. So where vertical asymptote happens. And we don't have any solutions for up there where that becomes 0 that are real numbers. So to the left over here, this will be positive divided by a negative will be a negative. Over here will be a positive. So it's continuous 1 to infinity. And that's my last example for these notes today. We'll come back next time and pick up on that second part of those techniques for computing limits, when we're going to talk more about limits at infinity next time in lecture 6. So I'll see you for the next video.